Hi there! In my last video I encountered some problems running Andy's machine code that I downloaded from his website, Andy's Machines, and I didn't go into any detail in the last video about what the problems were, but basically it would output signals and then suddenly it'd stop outputting signals, and then you change the gears, number of teeth in the gears, and then it'd stop again. It just wasn't working properly. So in this video I'll show you, or I'll explain what I did to address that problem, and I'll complete the build of the machine, and hopefully we can start cutting some gears. So the first thing to do is to acquire the hex file from Andy's Machine website, and then you connect the Arduino up to one of the COM ports on your PC or whatever, and the idea is that you download that hex file onto the Arduino. Now I'm following a different procedure to what Andy outlined in his instructions. I think it's being used by a few other people and it seems a little bit more reliable maybe. And it's to use something called Xloader, which is a program that's available from Hobbytronics. So you can download that, put that on your PC and run it. So that's running here at the moment. So that's open rather. Now the first thing to do is to look in your device manager and make sure that one of the COM ports is recognising the Arduino Uno. And that's telling me it's on COM 1. Now there's a strange thing going on here, because if I look at the properties and the port settings are set at 9600 bits per second. Now when using Xloader I've changed the baud rate to 9600. Most of the time it fails to upload the hex file. So if you leave it at that setting you get a better result and it works. I don't know why. So what you need to do is to make sure that you've selected the hex file. Make sure that the device is the correct device, so it's an Uno. Make sure you got the COM port right, so it's on COM 4. And keep the baud rate set at that, not 9600, and then upload. So that's it. Okay, so the supply voltage for the Arduino should be, well, they reckon between 7 and 12 volts, but Adam reckons that it can get quite hot on the board if you supply 12 volts. So I've got a wall wart on order that's supplying 9 volts in here, so just plug in there. And on this side we've got 5 volts which will be going to the rotary encoder, and a ground going to the rotary encoder, and this other ground will be going to the stepper driver, the pull minus and the pull plus. And over here A1, albeit it says analog in, these are outputs, so A1 is the step, and that will be going to pull plus on the stepper driver, and A2 is DIR, and that will be going to DIR plus on the stepper driver. And we've got a little LED there that needs to be connected to A4 and A5 the right way around. So all good so far, and that's how it was set up when I tested. Now on the other side, the instructions say that you connect pins 2 and 3 to the outputs from the rotary encoder. So I had connected one wire on that one and one wire on that one, so the green was actually on that pin, and the results I was getting were really odd. 1 minute it'd be outputting some signals, and next minute, even just switching power on, on my bench supply caused it to stop working. And I managed to contact Andy, who developed the code, and I sent him a video showing what the problems were, and he sort of got back to me very quickly and said he thought it was something to do with the signal or the signals coming from the rotary encoder. And on closer examination I realised that this pin here, which I thought was pin 2, is actually connected from the shield onto pin 1 of the Arduino. So this connection here is actually connected to pin 2. So I had it connected to pins 1 and 2 instead of 2 and 3. So I switched these up. Well, I moved this green one from this connection here up to this connection there. So albeit it's, you know, it looks like it's on 3 and 4, it's actually on 2 and 3. Having done that, it seems to work perfectly. So I'll hook it up temporarily and I'll show you the results. Okay, so this looks a little bit messy, but the wiring is set up as I've just previously described. Now on the stepper driver, I've set the current to a peak of 1.91 amps. I've set the switch 4 to half current, so that's off, and I've set the pulses per revolution to 200. So the gear ratio on my Hobbing machine is 3 to 1, so effectively that's changing this to 600 pulses per revolution going out. Now my rotary encoder has got pulses per revolution of 600. Now in the controller, the encoder CPR should effectively be 150 because it's a quadroshield encoder, but if I need to set it to 600 for it to work, so that's more like pulses per revolution coming from the encoder. And the stepper steps per revolution on the spindle is 600, as I've just described. It's 200 multiplied by 3, and the acceleration 5,000. I'm not too sure what that is, to be honest. And the stepper maximum of 4,000 steps per second. So we'll give it a try. So on here it'll show me the RPM, and that should match what's on the mill. So the mill's just reading, actually on the milling machine, 252 RPM, and that's coming in at 250, thereabouts. So that's pretty encouraging so far. And this divide by, this is the number of teeth that are going to be cut. So if we look at the scope here, just freeze that a minute. This is the incoming signal from the rotary encoder, and this is the outgoing signal, and so this is the one going to the motor. So you can see here that for every 20 inputs I'm getting one output, which is perfect because effectively it's on a one-to-one ratio. So in theory, if I put power to the stepper driver, we should get this rotating. Hey. And I have sort of manually counted the revolutions. and it's working spot on. So for every 20 turns of that spindle, I'm getting 1 turn there. So in theory, now, if I change on the fly the number of teeth I want to cut, so if I go, let me see, 16, see there, the 16 incoming pulses and 1 outgoing. If I change it to 24, it's actually gone off the screen there, hasn't it? You can count those, it'll be 24. It's running quite slow compared to that. And while I was at it, I made a little nameplate. Couldn't resist that. Okay, so as an experiment, I've changed the pulses per revolution on the stepper driver to 400. So effectively that means to turn the Hobbing machine a full revolution, it's 400 multiplied by 3, so it's 1200. So I've gone into here and set encoder still at 600, but the steps per rotation on the spindle is 1200, right? So what I would expect to see now is to cut 24 teeth. I would expect to see signals on the scope every 12 incoming pulses for 1 outgoing. So my speed is relating to the actual speed on the milling machine. Just freeze this. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. Absolutely perfect. Happy with that. Okay, so as a final test then, I've set the pulses per revolution on the stepper driver to be 800. So bearing in mind it's the 3:1 ratio, so effectively we need 2400 steps to go out to pulses to go out to maintain 1 revolution. So that's what I've set on the controller on the Arduino. So we'll set the teeth to, if we set it to 20, we should be getting, let's work this out, so for every, if it was a 1:1 ratio, 20 pulses coming in, 1 going out, but it isn't. So I reckon it's going to be 5 pulses coming in and 1 going out. Oops. It's pretty good. 1, 2, 3, 4, 5. Perfect. So I think I'm going to leave it at that sort of resolution. Okay, so I've made a box, and originally I designed it in Fusion 360, but when I generated the G code and found out it was going to take 22 hours, I went off that idea. So I've made one in wood, and I've got some inputs here. I couldn't resist sort of doing a bit of engraving as well. So that's 24 volts in for the stepper driver. That's on an aviation 2-pin plug, and there's 9 volts in there for the Arduino. And on this side I've got the outputs, and again these are aviation plugs, different number of pins in them, so I can't really get them mixed up. And so that's going to the rotary encoder, and that's going to the NEMA stepper motor. Well, that's turned out to be quite a tidy solution, and I can reuse this power supply for another stepper driver, so another project if I need to, using the same connection. And one thing I never did was to check the run out. Now that's looking pretty spot on. Now unfortunately that's about 1.5 thou out, which I'm a little bit disappointed in. But a way around that is I can put a 4-jaw chuck on here, an independent one. So that should get me around that problem if I need to. Well, the fantastic news is Andy, aka Andy's Machines, has just lent me the 48 dp hob. How cool is that? So I think what I'm going to do is I'm going to cut a couple of gears using the normal sort of gear cutters, and then I'm going to use the hob to make the same gear, and then I'm going to compare the two. Okay, so I thought it might be an idea to have a go at cutting one of the gears for the Jerry Howell V-Twin using the Hobbing machine. So I've cut some blanks, and bearing in mind these drawings are twice the actual size, and and I've also cut a mandrel. And the first thing to do is to tilt the mill head by the helix angle of the hob. Now on here for this 48 dp hob, it says that the helix is 1 degree and at 20 minutes. So I'll show you how I'm going to go about doing that. Okay, so if we view this drawing as that being perpendicular to the bed, and this is the spindle tilted at the appropriate angle. Now we would know that the angle down here that we're aiming for is 1 degree and 20 minutes. And if we move the spindle down by 1 inch, we can work out that distance there. So it's the sine of x equals y over the spindle movement. So if we move the spindle by 1 inch, sine x multiplied by 1 equals y. So sine of 1 degree and 20 minutes is equal to y. So y is equal to 0.02326 of an inch. So we can go over to the mill and have a go at adjusting it by that amount. Well, it's taken me about half an hour to get this right. So I've just put a gauge on here and just up against this angle. And if I move it down by 1 inch, I'm looking for 23.25 thou, and that's just on 0, and that looks spot on. So as a double check, I've just put this V block on the table, and I'm looking to make sure that those cutters are sort of exactly horizontal, and that looks pretty good to me. So I've used a bit of Loctite to fix the gear blank onto this mandrel, and what I need to do is, well, I've set this at the centre level, and it's just clearing the gear blank at the moment. So what I need to do is to set the controller to 21 teeth, which I have done, and if I start the machine, this should rotate. So now I need to advance the table that way until it just starts to make a mark. So you can tell this is just running slightly out by a couple of thou, but should be a reasonable test. So I'm sort of just touching it there. A bit more. A bit more. I'll keep on going until I can get a mark right round it. It's just about got it there. So I'll set the y-axis on 0. And I'll move the table that way. And this needs to go to a depth of cut of 45 thou, but I'm only going to cut in 10 thou increments. So if I move in 10 thou, lock the table, draw it back slowly. Draw the table back, go round again, and go to 20 thou, and repeat again. A bit of a disaster, and I don't know whether it's due to the fact that I've got the mill spindle set at 600 and the hob spindle set at 2400. I mean, I would guess that should work, or whether it's because I'm taking sort of 4 cuts of 10 thou or thereabouts. I don't know. Now Douglas in Pennsylvania contacted me and suggested that a digital microscope might be a useful thing to buy, and this has just arrived today, and I must admit I'm absolutely amazed for the price. It's quite an amazing piece of kit, to be honest. And this is the gear that I've just cut using the normal gear cutter and the World of Ward rotary controller, and the teeth on it look nicely formed, so I'm very happy with that. So the gear on the right is the one I've just made on the hob, so this is mild steel, and it was made using multiple passes, 10 thou each time or thereabouts, and as you can see the teeth just well, a right old mess, to be honest. Well, I'm pretty convinced that the hob is pretty rock solid on that mandrel, and also the blank is rock solid, so there's been no movement there. So what I've decided to do is I'm going to cut this in one pass. This is a piece of aluminium this time, the other was mild steel, and I've also changed the setup on the controller. I've set it up so there's 600 pulses coming in and 600 pulses going out. Oh, that looks like a far better result. So this is a gear I've just made, which is a really good result actually. So this is aluminium and a single pass using the Hobbing machine, and with it being a quick pass, it's worked out really nicely, and it engages with the other one that I've just made with the standard gear cutter. Engages quite well. So that looks like a good result. So in this test I've still got the controller set up for 600 for the mill spindle and 600 for the hobbing blank, and rather than doing one full cut, which is what I did last time, I'm going to do multiple cuts, so 10th out at a time. Now this gear was made on the hob. It's an aluminium gear, and this was created by making multiple cuts, about 10th out at a time. And I think it's a time issue, because you can see that these teeth are malformed. They've got a bit of a curve on them, and as opposed to the first one, the first aluminium one I cut, that was a very quick cut, and that turned out really nice. But with this having sort of 4 or 5 passes on it, it's taken longer to actually make this gear. So you can see it's like a sync problem. Very odd. Now this gear on the right, that's made out of mild steel using the hob, and with it being mild steel, it took a lot longer to cut this as a single pass compared to the one made out of aluminium. This is the one that was made we're using the normal cutter, and as you can see over time, it's gradually lost synchronization, and the teeth are really pointy. Very odd. And as a comparison, this is the one that was made on the hob out of aluminium. Single pass, and that's a single pass on mild steel. Well, that seems to be a bit of a brain teaser. This sync problem is a consistent thing. It's not like the pulley wheels are slipping. I mean, I've checked the pulley wheels. They're okay. They're fine. I've checked that the hob is, attached to that mandrel, and there's no movement in that. And when I've attached the blanks to the gear blanks to the mandrel, they've been rock solid. So I don't know what's going on. Really odd. So I think I need to think about this overnight, and maybe something will spark to life in my brain. Because I can only think it's something I'm doing wrong. But the good news is that digital microscope is fantastic. I don't know how I would have got on without that, because it really does highlight in detail the profile of the gears. So can't thank Douglas enough for that suggestion. But anyway, I hope you enjoyed the video, and I hope to see you later.